A little bit late today, but basically we're talking about Lewis structures today, which you guys know how to do Lewis structures, I hope. Or if you don't, you will soon, because I think it'll come right back to you. So this is 8.5 to 8.7. We're moving through the back half of this really fast because I stopped and needed to take time with the PES stuff because that's brand new. The rest of the stuff we're covering in this unit is going to be basically review. I guess 8.8 is a little different, but we've already talked about bond breaking and bond formation, so it shouldn't be that difficult for you. All right, so first of all, 8.5 is about drawing Lewis structures in general, okay? So I'm going to pick one of these. Let's do sample exercise 8.8 on page 316. Need a book. Okay, 8.8 on page 316 because that's a good one. And honestly, you don't really need to be looking at the book for this, I guess. You might need it for a future problem in a minute. But we're going to draw the Lewis structure for the Br03 minus ion. Okay? So this will be a good review of kind of all of the things that you need to be thinking about when you're drawing a Lewis structure. Not all of the things, I guess, because we're not going to end up with any double bonding or anything there. Sorry, page 316. All right, so the way that this works, when you're doing a Lewis structure, you just have to remember that the least electronegative atom is the one that goes in the middle, okay? Now, do you remember how we figure out which one is the least electronegative? Well, we did have a chart, but yeah, the ones that are on the left side and further down are the least electronegative. Now, there's another way you can tell when you're looking at something like this without even looking at the periodic table, just by looking at the formula itself. You remember the general rule? It doesn't always work. The general rule is the atom that's listed first is usually the one that goes in the center because it's usually the least electronegative, okay? That doesn't work with something like H2O. No, yeah, it does. Yeah, it does. Except in H2O, anything with hydrogen, you have to put, it doesn't go in the middle, but it is the least electronegative, right? Because in this one, you'd put the hydrogen on the outside. But you always do that with hydrogen because hydrogen only wants 2 electrons, right? So the exceptions usually happen with hydrogen. All right, so Br03 minus, Br is going to be in the middle, okay? And then you just put the oxygens around it. Doesn't matter where because we're not talking about shape yet, okay? And then you count the total number of valence electrons that we have here. So how many valence electrons do we have in this particular polyatomic ion? Okay, so there's 24 from the I'm sorry. What am I doing? There's 18 from the oxygens. There's 7 from the bromine. That gives us 25. Kind of an awkward number, right? But we do have a minus charge here, which means we have 1 extra. So there's 26 total electrons here. All right? 26 valence electrons, I should say, that we're working with. You only count valence electrons when you're doing this. Then we're going to put electrons to make the bonds, right? So that takes care of 6 of them right away. That leaves us with 20. You remember what the next step is, where we put electrons next? You put them around the outside atoms, okay? 3, 4, these aren't going to look like dots, sorry. 10, 11, 12, 13, 14, 15, 16, 17, 18. Now you used up 18 of our electrons. Now we have 2 left. And any you have left, you just put them on the central atom. Remember, even if that gives the central atom more than a full octet, okay? Even if it gives it more than 8, you can dump them on the central atom. Now, if you run out of electrons and not everything is happy, then what do you have to do? Remember? Then you would do double or triple bonds, right? Okay? So extra electrons are not a problem. Just dump them on the central atom. If you don't have enough electrons to give everything a full octet, then you have to start thinking about double and triple bonding. Okay? Now, the one thing that everyone always forgets, this is a polyatomic ion, so it needs to have the brackets around it with the minus charge. Okay? So that's how you draw a Lewis structure for BrO3 minus. All right? The one that they show on the page before that is Lewis structure for HCN. That one might be worth doing just, and that's sample exercise 8-7 on page 315. Okay? So HCN, that's a little tricky because there's 3 atoms there, so what do we put in the middle? But what you have to remember, I mean, there's one that's out of the running already. We cannot put it in the middle. Which one is that? Hydrogen. Can't put that in the middle, right? So it's between carbon and nitrogen now for the central atom. And if you look at where they are, nitrogen is closer to the right, so it's more electronegative, which means we want carbon to be in the middle. Okay? So we'd put H, C, N, basically like that. Again, it doesn't have to be like that because we're not concerned about shape yet, but you have to put the hydrogen and the nitrogen around the carbon. Okay? So then we count up our valence electrons here. We've got 10, right? 1, 2, 3, 4. That'll leave us with 6. And then we need to put those around the outside atoms, except we don't put them around hydrogen, because hydrogen's already happy. 1, 2, 3, 4, 5, 6. Well, carbon's not happy, is it? Not happy at all. But we ran out of electrons, so this is an example of where we'd have to do a double or a triple bond, right? How many more electrons does carbon need in order to be to have a full octet? It needs 4 more, okay? Now there's really no electrons to give to the carbon from the hydrogen over here. It's got to come from the nitrogen. So basically I'm going to take 2 of these pairs, put them in the center here, and then I'm going to end up with something that looks like that. Is it coming back to you? Okay. So, well, let's, oh, sorry. Thank you. Should have the 2 extra electrons on the nitrogen. So then you just, this is not a dot down here. That I don't know, it looks like a dot, but that's not. I mean, it is a dot. It's not supposed to be there. So 2, 4, 6, 8, 10 on the nitrogen, or on the whole structure. And each of them, the nitrogen is happy because it has 8. Carbon is happy because it has 8. Hydrogen is happy because it has 2. None of them are really happy. They don't have emotion. So anyway, I thought I'd make sure and clarify that.
Did you insulted that dot?
Yeah, sorry. That is a dot. You're there, buddy. You're there. You're not supposed to be there, but why am I talking to him? I just said they don't have emotion. Okay. Anyway, let's just erase that.
That's even more hurt.
No, it doesn't exist anymore. Okay. Now we need to talk about something called formal charge that we did not talk about last year. Okay. Formal charge is kind of a useful thing, and this is the one kind of new thing from this set of sections, I guess. So you've got something like on 317, sample exercise 8-9. It says there are 3 possible Lewis structures for the thiocyanate ion NCS-. Almost a TV show. So it shows you the 3 structures down there. I'm debating about whether I need to draw all 3. I guess I probably do, because then we can actually evaluate the formal charge on them. N, C, triple bond, S, and then it's got 6, this. Okay, so that's one of the possibilities. Another possibility is 2 double bonds. Then I'm going to have to write the other possibility down here. A triple bond with the nitrogen. A single bond with the sulfur. Okay? Any of those are actually acceptable following the rules of drawing Lewis structures that we learned last year. Okay? Because all of those make everything happy. They use the right number of electrons. So the question then is, how do we know which one is actually what forms in real life? Okay? So the idea here is it's very much related to how electronegative these things are. Okay? Things that are electronegative tend to want more electrons. They tend to not want to share in double and triple bonds as much. Okay? Things that are less electronegative tend to be more willing to form double bonds and share their electrons a little bit more. Okay? So there's this concept called formal charge. And the rules for formal charge, and it has the rules on page 316. It says all unshared electrons are assigned to the atom on which they are found. Okay? So in other words, these electrons on this nitrogen, these electrons, and these electrons, they all belong to the nitrogen. They're not sharing, the nitrogen is not sharing those electrons with anybody else, right? Anything else. I keep giving these things personality. Anytime you have a bond, you give half of the bonding electrons to each of the atoms in the bond. Okay? So, for example, this carbon-nitrogen bond right here, there's 2 electrons there. We're going to say one of them belongs to the nitrogen, one of them belongs to the carbon. All right? So that's how you're going to assign formal charge to these things. Okay? And then basically you compare the number of valence electrons that this thing normally has with the number of electrons it has around it in this Lewis structure, and you want them to be close. You want them to be similar to one another. All right? So the idea here, I'm going to have trouble erasing this without erasing other stuff. Let me see if I can. I'm just not going to erase this arrow over here. All right, so we're going to assign formal charges to these and see how we do. So this nitrogen right here has how many electrons assigned to it? 7, right? Okay. 2, 4, 6 from the unshared electrons, and then 1 from the bond right here. So that's 7. Okay. Now, how many valence electrons does nitrogen have? It has 5, right? Okay. So what you do is you take the number of valence electrons minus the number of electrons it now has assigned to it, and that gives you its formal charge. Okay. So the formal charge on this nitrogen right here is a -2. Number of valence electrons minus the number of assigned electrons. Okay? Now what about the carbon in that particular structure? The carbon has 4 electrons assigned to it. How many valence electrons does it have? Okay, and that's good. That's what we're shooting for. 4 minus 4 is 0. We want everything to have a formal charge of 0. In the most stable structure, it will, or close to that. Okay? Now what about the sulfur over here? How many electrons does it have assigned to it? 5. Whoops, sorry, wrong way. Start with the valence electrons. How many valence electrons does sulfur have? 6. Minus the 5 that are assigned to it gives it a +1, right? Okay? So in this Lewis structure, nitrogen has a -2 formal charge. Sulfur has a +1 formal charge. That's not exactly what we're looking for, okay? That means the nitrogen in this structure kind of has too many electrons, and the sulfur doesn't quite have enough. All right? So let's try this second structure over here. The second structure, what's the formal charge on the nitrogen? It's 5 minus 1, 2, 3, 4, 5, 6, right? It has 6 assigned electrons there. Okay? So 5 minus 6 would be a -1 for the formal charge on that nitrogen. Carbon's still good, okay? Carbon has 4 electrons assigned to it, so it still has a formal charge of 0. And then the sulfur here has a formal charge of 0, right? Because it has 6 electrons assigned to it, and it has 6 valence electrons. That one's looking pretty good, all right? Now the nitrogen's not, it maybe has a little bit more electron density around it than it typically likes, but that's not a bad structure, okay? Then the next one over here, we've got nitrogen with a formal charge of 0. Can we see that? Okay. Carbon has a formal charge of 0 still. Sulfur has a formal charge of -1. Well, it seems like we've got two fairly equivalent structures here, right? Okay, so it seems like the one that's more electronegative probably would be more willing to have the -1 charge, right? Now this is tricky because nitrogen and sulfur are diagonal from one another, okay? So you might have to look at a chart ultimately to decide which one of those is more electronegative. I'll give you a hint. When hydrogen bonding occurs with things that are fairly electronegative. And there are three elements that hydrogen bonds with, right? What are the three? They're Fon, right? Okay, fluorine, oxygen, and nitrogen. Oh, nitrogen. Okay, so probably this is our best structure. Let me check in the book and make sure that that's right. Yeah, nitrogen is more electronegative, so we would expect that the negative formal charge would be on the nitrogen atom. Okay. Right. So the things that are more electronegative, they want their own electrons. They're going to be the ones that tend to want to pull electrons to themselves and not share as much with double or triple bonds. Okay. So that middle structure is probably the better of the three. Okay. This one right here, we can probably say with confidence that the one on the far left doesn't form in real life. Okay. Because it's too off. And then honestly, probably this one doesn't either, because if the electrons are going to be more around anything, it's probably going to be the nitrogen, not the sulfur. Okay? So that's the idea of formal charge. Resonance is another thing that we have to think about. Do you guys remember resonance? Okay, I'm going to run through that very quickly. What time are we at here? Run out of time fast. Okay, I think I have time for this. So again, I'm going to do this fast, so hopefully this makes sense. So resonance would be something like sample exercise 810 on page 320. Okay? So you've got SO3 and you've got SO3 2-. Okay? The one that's going to have resonance, I'm just going to give away the punchline here, is just the SO3. That way I can show you a resonance structure. So when you set this up, you've got sulfur and 3 oxygens. That's a total of 24 valence electrons that we're dealing with here. 2, 3, 4, 5, 6 of those go in the middle. That leaves us with 18. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Well, we got a problem because sulfur's not happy, right? So what we have to do here is from one of the oxygens, we need to make a double bond. Then the sulfur has enough. Problem is, which oxygen? They're all pretty much the same, right? Okay, so really, whoops, what am I doing? Sorry, I was in the middle. This is where you have to draw them all, okay? And this is not, I just want to be clear here, and we're going to talk about this more in the next unit. This is not right, okay? This is where the Lewis model breaks down, okay? Because what's really happening here, and we talked about this a little bit last year, is more of a 1 1/3 bond between each of the sulfurs and oxygens. Those electrons, they end up getting delocalized is what happens. So they're kind of equally shared throughout all of these bonds right here. To understand how that happens, you got to remember sigma and pi bonding, which we talked about a little bit last year as well. We're not going to get into that until the next unit, all right? So for now, you just need to understand that when you have something like this, you have to draw all three structures, okay? because Lewis got his model wrong just a little bit. So then you'd have to draw the other two possibilities with the double arrows, okay? Then the other thing that's in here is exceptions to the octet rule. We're not going to worry too much about odd numbers of electrons, which they talk about on page 322. Less than an octet on page 322. You remember the one atom that's usually okay with having less than 8 valence electrons? I know, this is just kind of straight memorization stuff. Boron, right? Remember boron the moron? Only needs 6 valence electrons, not 8.
They weren't here.
Oh, okay. You might not have been. Anyway, so boron, well, no, but we talked about this last year. Yeah, pretty sure. So boron's okay only having 6 valence electrons. It's one of the only atoms that really is. Okay, so you got to remember that exception. And then the other exception that's in 8.7 is when you have more than an octet. Okay, now, do you remember... do you remember which ones can have more than an octet? It's the ones that can't have more than an octet. Everything in the first 2 rows, right? They're too small. They can't have those expanded octets. But 3rd row and below, they can have an expanded octet. And that's where we talked about this rule already, where if you have extra electrons when you're drawing your Lewis structure, just put them on the central atom, as long as that central atom is in the 3rd row or below, okay? Now, the reason I gave you for that last year was because of the d orbitals. That is in the process of being disproven right now.
Class live.
Yeah, so that one I lied to, and actually I think I maybe even mentioned this last year, that possibly might not really be happening. There's a big group of chemists that are becoming fairly certain that d orbitals are not involved in those expanding octets. So there's something else going on there, okay? Just, just for fun on that one, okay? So all you need to know basically is 3rd row and below, they can expand their octets. You don't need to know why, because we're still kind of figuring out why, okay? All right, so that's that. That was kind of a fast one, but it's review, so hopefully it'll all come back to you. All right, see you guys on Monday. Have a good weekend.